There we go. So we're in chapter 4 talking about maxes and min value. On Wednesday, we went over essentially the process for how to find our maxes and mins. So remember, we have these things called critical points, where that's going to be where our derivative is 0 or undefined. Which remember, undefined in our case is going to be that denominators are 0. We went over the full process for how to find these local extrema using the first derivative test. We did get to one small example, but we didn't get to like a fuller one, so that's what we'll start with now. So we did this kind of small example with x cubed. We found its derivative, set it equal to 0, plotted its points. Remember, we're going to be using these kind of derivative number lines, if you will, and that's how we're going to find if they're a max or a min. We're going to look at the sign of the derivative. So let's start with, we're going to skip past the second derivative test. We'll come back to that right after this example. But I want to do a more full example of the first derivative test on this one. So let me reshare my screen really quick, just in case. All right, so say we want to find all the local maxes and mins of this function. So to kind of remind us what we're doing, I'll kind of write the steps along the way too. So the first thing we do is we find our derivative. Find derivative. In this case, that's going to be a quotient rule. It's not a particularly tricky quotient rule, but it is a quotient rule. So if I do my little chart over here to try to save space on the rest of the problem, we'll have that f is x and g is x squared plus 1. F prime is 1, g prime is 2x. And of course we'll need g squared, but just to save the tiny little space, I won't write it in the little chart, and I'll just put it in a derivative. So if we put that together, we have f prime times g, so 1 times x squared minus f times g prime, all over g squared. Now, usually with the general derivative questions, I told you didn't have to simplify, but I do think I said something about in chapter 4 we were going to have to simplify a little bit. So we want to simplify that numerator a little bit. Yeah. Can reshare. There we go. Come on. There we go. So what was I doing? Simplifying the numerator. We're going to simplify the numerator a little bit because it's going to make the next step easier. So I'm going to simplify the numerator. I'm going to do it over here, and I'm also going to write that note that I'm simplifying the numerator so we don't think that I just dropped the denominator or anything. So that x times the 2x is going to give us minus 2x squared. So that's going to reduce to, whoops, sorry, way back when I was putting x minus 1 instead of x plus 1. So I'll write those fixes in red so you can tell what I changed. So sorry, the g was x squared plus 1. For some reason, I just had changed it to x squared minus 1 by accident. Anyway, so when we simplify this, we'll get 1 minus x squared. Because the x squared minus 2x squared will give us essentially negative 1x squared, so we can write it like that. So then I can rewrite my derivative as 1 minus x squared over x squared plus 1 all squared. I'm going to try to remember to pause every once in a while to let y'all catch up. So once we've found the derivative, this is where we need to find our critical points. So find crit points. We're going to have essentially 2 situations for this derivative because we need to find where it's equal to 0. And in this case, since there is a denominator in this derivative, we're going to have to check for when it's undefined as well. So remember, I said that for a function to be undefined, it can be undefined in a ton of different ways. But in our case, we only care about denominators. So when we have a denominator, we need to make sure we check when it's 0. So that's resharing. There it goes. What do we do? So f prime equal to 0. So we take our derivative, 1 minus x squared over x squared plus 1 all squared equal to 0. If we wanted to start solving this, we would take this entire denominator and multiply it to the other side. Anything times 0 is, of course, 0, so we just end up with 1 minus x squared equals 0. If you want, there's kind of a shortcut. It's barely a shortcut, but if you want to like skip this step, it's fine. So for a fraction, it will equal 0 only when the numerator is 0. So if you have a fraction as your derivative and you want to set it equal to 0, and just setting the numerator equal to 0. So we add x squared over to the other side. And then we square root both sides. Now remember, back to algebra, when you square root something, the answer is technically a plus minus whatever the square root of that would be. Because if you think about it, -1 squared is still equal to +1. So we do need that answer of -1 coming in. One of my screens is super laggy. Come on, buddy, you can do it. So we get that the derivative here is 0 at positive and -1. So we'll hold on to that for a second, kind of keep that in the back of our heads. And now we need to see when the derivative is undefined. So we take that denominator and we set it equal to 0. Now, there's kind of a special thing that's happening in this case, and if you kind of see what's already happening, you can just kind of say the answer. But if we wanted to go through this fully algebraically, we'd have to square root both sides to get rid of that squared on the outside. I don't necessarily write the plus minus here because +0 is the same as -0 because 0 doesn't have a sign on it. Subtract 1 from both sides. Now here you would technically want to square root a negative, while in general mathematics that exists. It's an imaginary number. In terms of what we care about, our graphs don't work with imaginary numbers, so this never happens. Never happens. So essentially what that means is that we just don't have any more critical points from that part. So it's okay that we came out to nothing in that piece. It's just that that means that the only critical points we have were at the plus minus one that we got from setting it equal to 0. So we're not done yet. These are somewhat long problems. The undefined thing on the left. So, okay. Either, I'm not understanding your question. Okay, on the right. Okay, I was highly confused. I was like, the undefined's on the right. Okay. Generic function that has nothing to do with this question. This is a super side note. Say you have the function 2 over x, and I wanted to plug in 0. You can't plug in 0 into a denominator. It makes the world explode. And that would be considered making that function undefined. So way back the other day, we had this definition. Come on, scroll for me. There we go. And catch up to me, screens. There we go. So the other day we defined the critical point, and the critical points can either happen when the derivative is 0 or undefined. And if having a 0 in the denominator makes a function undefined, that's what we need to consider. So since the derivative that we have in this question does have a denominator in it, we need to check to see where it's undefined. It never happens to be undefined because x squared plus 1 all squared is never equal to 0, but that's why we check, because that is a possible place for a critical point, because we have a derivative, which would mean that, sorry, we have a derivative, because we have a denominator, and denominators being 0 would make something undefined. Any sense? Okay, cool. So the only time you have to worry about this thing on the right is when your denominator and derivative, I keep mixing them up. You only have to worry about it when your derivative has a denominator. If your derivative doesn't have a denominator, which is going to be like the vast majority of the ones we actually work with, this is kind of a special case. So most of the time you won't have to worry about it because there won't be a denominator. But if there is a denominator, we got to do it. All right. So we found the derivative, we found the critical points, but now we need to figure out if these critical points are actually maxes or mins. Because remember, we can have critical points that aren't maxes or mins, so we have to triple check whether these are or aren't. And I've run out of space. I write too big. It's okay, I can squeeze it down here. The way we do that is a number line. Let me get myself a tiny bit more space and rewrite this. Kind of do an arrow this way. This would mean that x is plus or minus 1. There we go. Now I got a little bit of space. And if I move this, it happens. There we go. A little bit of extra space. So this is when we do our number line. So we draw a number line, and our 2 points that we're working with are positive and negative 1, so we go ahead and slap those on there. And now we choose our test points. So since I have an option of choosing another color, I like to do it in another color, but also I like to put them with a kind of different kind of label. I kind of label it with it looks like an I instead of just a slash so that I remember, because you need to remember which ones are your test points and which ones are your critical points so that you can get the answer right. So try to differentiate between the two on your number line some way. So I need a number to the left of -1, so something less than -1. You can pick whatever you want. I'm going to pick -2. Something between -1 and 0. -1 and 1. I'm going to pick 0. And then something greater than 1. I'm going to pick 2. It does not matter what number you pick. The answer should still come out the same as long as you've done everything else correctly. So once we have those test points, we're going to take those test points and plug them into the derivative. So we're going to plug in -2, we're going to plug in 0, and we're going to plug in 2. And we're plugging them into the derivative because we want to figure out what the sign of the derivative is, which is also why I put this little f prime kind of label next to the number line to remind myself kind of what function I'm using. Let me scroll down a little bit so that our derivative comes back in here. The derivative was up here. So we have 1 minus 2 squared. So -2 squared. So 1 minus 4 will give us -3. -2 squared plus 1 will give us 5. And then we square that. This will be a negative number. I don't even care about the final answer. It'll be -3/25. But I don't really care about the actual number. So if you can kind of stop once you see where the sign of the derivative is going to be, we are taking these, and where yellow is probably not the best choice for that, but hopefully. And we're plugging it into the derivative, which is up here. The 1 minus x squared all over x squared plus 1 all squared. If we plug in 0, 1 minus 0 squared is 1. 0 squared plus 1 is 1, all squared. That's going to be a positive number. Oh, I meant to do something before I plugged in the next number. Oh, well, I'll just keep doing this then. And then if we plug in -2, we'll get 1 minus 2 squared. So 1 minus 4 is -3. 2 squared plus 1. So 4 plus 1 is 5. So we'll have 5 squared in the denominator. That's negative. So when I plugged in -2, I got a negative number. So let me put a negative kind of on top of that -2 on my number line. When I plugged in 0, I got a positive number. That's a really bad plus sign. I tried to make it thicker and it didn't work out. There we go. A little better. And then when I plugged in +2, I got a negative number as well. So now we can figure out whether these points are a max, a min, or neither. So one thing I like to do is I like to kind of take the idea of whether the derivative is positive or negative and remind myself what that means about the original function. So at that kind of -2, the derivative is, which means that the original function would be decreasing. So let me draw this like little decreasing line segment there. And then between -1 and 1, the derivative was positive. So that means the original function would be increasing. So let me just draw a little increasing piece. This is unnecessary, but I think it's helpful to see the answer, so I like to do it. Technically, once you have the signs on that chart, you just got to think about what that means and be done. But anyway, and then from 1 onward, the derivative is negative, so the original function would be decreasing. Once you have that number line and you have all the signs and your optional little line segments, we can figure out whether these are maxes or mins. So at x equals -1, the derivative changes from negative to positive, so the original function changes from decreasing to increasing. So we're going to have a local min there. So we have a local min at x equals -1. And then at x equals +1, the derivative changed from positive to negative, so we went from increasing to decreasing on the original function. So we have a local max at x equals +1. And now we're done. So like I said before, these ones they are a bit long. They're pretty long questions, work-wise, but questions, concerns about any of that? I'll hold on a couple seconds in case someone's typing something, and then we'll talk about the second derivative test. I think it's fun, but Juliana, so also the other day, scroll. So if I go back up and I look at this theorem that we talked about the other day, this essentially tells me that if there's a local max or min, it must have been at a critical point. So if we have a max or min, then it must have been a critical point. So essentially what we do is we say, okay, well then why don't I find all the critical points and then see if it's a max or min. So that's why we found the derivative and set it equal to 0 and did all that undefined stuff, because those are essentially all of our options. If there's going to be a max or a min, it has to be at one of those points. It can't be anywhere else. And if you think about it, if you think what we were talking about, I think this was Monday, but way back when we were talking about this guy back here, and we located the max and the min, graphically, think about what the derivative is equal to at max or min. The derivative of those points would have, well, we'd have a tangent line that's purely horizontal at a max or min, and the derivative, the slope of a completely horizontal line is 0. So that means that these maxes and mins, our derivative is 0. And that's one of the options for our critical point. So it's essentially, we know that that's where the maxes and mins are going to be and nowhere else, because the derivative has to be 0 there. It could also potentially be undefined. That usually never gives you a local max or a min. It gives you like a different point of interest. But that's kind of how we know, is that we know that at a max or min the derivative must be 0. So why don't we find all the places where the derivative is 0 and then triple check that it's actually a max or a min using that kind of number line. So since that x equals +1 and -1 were the numbers that gave me the derivative equaling 0 from this critical point step, since those are the points where the derivative was 0, they're possibly maxes or mins, and then the number line confirmed it. So that's kind of why this works. Which is also why you got to keep track of your critical points versus your test points, which is why I personally put them in different colors, because the critical points can only, the extrema can only be at critical points, can't be anywhere else. All right. So you find the derivative and set it equal to 0. Yes, Jay, that's how you find your critical points. You find the derivative, you set it equal to 0. If it has a denominator, you have to set the denominator equal to 0 too. But the vast majority of the examples we'll do don't include denominators. I know this one did, but most of the ones we deal with don't have denominators. Oh, I always forget. All right, so let's go back up here and talk about the second derivative test. So remember, I know, breaking this up over multiple days, when we were talking about the process for local extrema, kind of this third step is choose which test you want to use. Most of the time we'll use the first derivative test, but there is something called the second derivative test that you can use also. So let's see how that would work. So the second derivative test for local maxes and mins. So the second derivative test says this. So also, sorry, scrolling back up again. Remember, for all of these extrema questions, you always have to find the derivative and find the critical points. No matter which test you use, that's always your first step. Find the derivative, set it equal to 0, see if it's ever undefined. You always do that no matter what test you're using. Okay, now let's write it down. So the second derivative test says this. You're going to find the second derivative. Have we found one of those yet? You literally just take the derivative of the derivative. Just like we've been doing, we have a function, we find its derivative, just take that derivative function and find its derivative. You're going to plug each critical point into the second derivative and find if it's positive or negative. You don't need a sign chart for this one, so there's no number line with the second derivative test. I should say P is a critical point for these last three pieces. So essentially you take that critical point and you plug it into the second derivative. If the second derivative is positive, now this one takes a little thinking, even for me, I always have to pause for a second and make sure I don't get it wrong. So if the second derivative is positive, remember that the second derivative tells us about concavity. So if the second derivative is positive, the function would be concave up. So it would look like, well, look something like this maybe. So if you think about it, that would actually give us a min. So we'd have a local min. Because the function would be concave up, so it looks like our little cup option. And essentially that point would end up being the bottom of the cup, essentially. Where if the second derivative is negative, we're concave down, so we would end up being kind of that maximum point. So we would have a local max. Now, this last piece is kind of why the second derivative isn't as recommended as the first derivative test, because if you plug in that critical point and you get 0, the test is inconclusive. And then you have to use the first derivative test anyway. So that's why most of the time you just default to using the first derivative test, because, what if you use the second derivative test and it just gives you 0 and then you have to use the first derivative test anyway. Also with the second derivative test, it's mainly used if the second derivative is easy to find. So in some cases, like the one we just finished, finding that second derivative would have been horrible because that would have been another quotient rule. And it would have had a chain rule inside of it, so that would have been pretty gross. But in some cases, like in example 2 we're going to look at in just a second, just a polynomial, those ones are usually pretty safe to use the second derivative. So let's see how this would work. Let me try to keep the last bit here. There we go. So let's try to use the second derivative test to confirm that that function has a local max at x equals -2 and a local min at x equals 8. So we kind of are told where these extrema are, and we just want to triple check that they're telling us the right thing. So, well, I'm going to do a bit more than this question is asking, just for review sake. But so we take x derivative, 3x squared, 9 times 2 is 18x minus 48. Now, say we weren't told what the critical points are, and this is where I'm going to do a tiny bit more than this question is actually asking for. They're giving us the critical points of -2 and 8, but just for review purposes, in terms of doing more questions like these, remember you can factor. So all of those terms have a 3 in it. Essentially, they're all divisible by 3, so we can take a 3 out. And then also maybe look up a refresher later on factoring. We could factor this, or you could use the quadratic formula. And sometimes you do need to use the quadratic formula because it can't factor. Formula, side note. So super duper side note is your negative b plus or minus the square root of b squared minus 4ac. This is getting a little plus minus 4ac all over 2a. And that's for some ax squared plus bx plus c. Sometimes you'll need that. That x does not look like an x. It's, well, it's being squished together with the b. But here we could factor this. What are two numbers that add to -6 and multiply to -8? You would get -8 and +2. So this would break up into x minus 8 and x plus 2. So essentially, if we were to set this derivative equal to 0, since these three things are being multiplied together, one of those pieces must have been 0. And essentially, that's where they're getting the x equals 8 and x equals -2 from. Again, this question wasn't asking me to do that because they were already giving us the values, but just for refresher purposes, that's how you'd find them. But what we were asked to do is use the second derivative test, so we need the second derivative. So we're going to take the derivative, whoops, we're going to take the derivative and we're going to find its derivative. So derivative of 3x squared, that would give you 6x. Negative 18x would give you 18. Derivative of -48 would be 0. So now that we've found the second derivative, our second derivative test says to plug in those critical points. So the critical points were 8 and -2. So we'll plug in those two values to the second derivative. So 6 times 8 minus 18. So 48 minus 18 will give you 30. 30 is a positive number. So I always like to remind myself, so positive would mean concave up. So this would be a local minimum, which is what they told us it should have been. So check that. And then 6 times -2 minus 18 will be -30. Coincidentally, the same number, but just different signs. That's not always going to happen, but. So that's negative, so that means we would be concave down. So that means that -2 would be a local maximum, which again, they already told us and we were just triple checking. But they were right. So that's how you use the second derivative test. You find the critical points and then you find the second derivative and take those critical points and plug them in. Again, if you can find the second derivative easily, it's kind of a nice test to use, but sometimes it doesn't work, and sometimes it's super hard to find the second derivative. There was a couple ambulances that apparently were going around outside of my office. Yes. So Kayla, -2, when I plugged in -2 to the derivative, I got -30 as an answer. And that means that the second derivative was negative. If the second derivative is negative, remember way back when talking about the second derivative tells us concavity, the second derivative is negative tells me I'm concave down. Remember concave down, looking over here really quick, concave down has to look something like this. So if the function is concave down at that point, so it looks something like that, that point must have ended up being a maximum. It essentially ends up being the middle of the concave up or concave down piece, which is why, yeah. And so with f double prime of 8, it was concave up, so concave up looks like this, so it must have ended up being a min. So I know it almost seems backwards to how you would like it to work out, which is why I always have to pause and kind of think about my little concave up, concave down kind of picture to be able to make sure I say the answer right, because that can get a little tricky. Okay, any more questions on the second derivative test? Go once, go twice. Okie dokie. So your personal preference on what derivative test you want to use, but again, it's suggested to just default to the first derivative test because, again, sometimes the second derivative test doesn't work. Sometimes it's super hard to find the second derivative. So it's usually just do the number line one. Come on, scroll. Let's see, 12:30. Okay. Use whichever derivative test we like to find the local maxes and mins of this function. We're probably just going to default to using the first derivative test again. And I'll show you why. It's kind of, the second derivative would be a little, not necessarily tricky, but just not worth our time to find. So first thing, find the derivative. This is a chain rule. We're in a something to the power situation. So power rule first, bring the power down, subtract 1 from the power. That inside piece stays itself. And then we have to multiply by the derivative of the inside. The inside is x squared minus 4, x squared minus 4. So its derivative will be 2x minus 0, essentially. While it's not really helpful per se for the simplification for this one, but I'm going to go ahead and multiply that 7 and the 2x to get 14x. It doesn't really help here like it did in the last one, but it just makes it look a tiny bit nicer. So there's our derivative. So we have to find our critical points first. No matter what derivative test we use, we have to find the critical points. So we have to set this derivative equal to 0. So we'll have 0 equals 14x, x squared minus 4 to the 6th. So whenever you have things that are multiplied together, in order for that multiplication of things to be 0, one of the pieces must have been 0. You can't multiply two numbers together and get 0 unless one of them was 0. So we essentially can break this up into its kind of pieces of that multiplication and set them both equal to 0 separately. Divide both sides by 14. For the one on the left, you'll get x equals 0. 6th root both sides, but it's okay because the 6th root of 0 is 0. It's not as complicated as if that weren't 0. Add 4 to both sides. Take the square root, and remember when you square root a number, you get a plus minus. So we end up with x equals 0 and x equals plus or minus 2. And maybe I'll just star a little note that says never undefined because there's no denominator. You don't really have to say that, but just to remind us that I technically considered it, but we didn't need to do anything because there's no denominator in this derivative. This is the point where you get to choose which derivative test you want to use. Since my derivative would, taking the derivative of 14x times x squared minus 4 to the 6th would be a principal. I personally think that's not worth the time to use the second derivative test on, and I would say just use the first derivative test. So we have 0, -2, and +2. We've got to pick some test points. So we've got, I would choose -1 and +1. And then I'm going to go ahead and choose 10 and -10, because why not? I want to. Doesn't matter, choose whatever number you want. Sometimes going a bit obnoxious can make it easier to figure out because you don't necessarily need to know what the actual number is. You just need to know the sign of it. So especially on those endpoints, going a little larger can make that easier to do. But whatever floats your boat, you can always just plug it into our calculator. So we need to take all of those test points and plug them into the derivative. I'm gonna regret that if I don't leave myself more space for my little lines that I like to put. Come on, erase. So f prime of -10, f prime of -2, f prime of -1, f prime of 1, and f prime of 10, which is another reason why I like to do them in different colors, because I almost made the mistake of plugging in the wrong thing. So we'll have 14 times -10. -10 squared will be 100 minus 4 to the 6th. Juliana, because I felt like it. That's literally the only reason. I just felt like choosing 10 and -10. I did say that sometimes choosing larger numbers can make figuring out the sign easier, but for the most part, I was just like, I'm going to pick 10 and -10. But here's what I mean by it making the sign thing a little bit easier. If I think about just the signs of these pieces, I have a positive number times a negative number. And then what I'm going to get here is I'm going to get a positive number to the 6th power, which will still be positive. So I essentially have a positive times a negative times a positive, which will give me a negative. So this is what I mean by you don't necessarily even have to know the number. If you just want to look at the signs of the numbers you're going to get, you can totally do that. But in case, what the heck is this actually as a number? I don't know. I haven't calculated it because I just used the signs. But this would, oh, that's a large number. Oh, that's a very large number. If you type this into a calculator, you get negative 1.09 blah, blah, blah times 10 to the 14th. But again, don't care what the number is, just care about the fact that it's negative. If I plug in -1, we'll get 14 times -1. -1 squared will be 1 minus 4 will give us -3 to the 6th. Now that would be a positive times a negative times technically a negative to the 6th, which would turn into a positive, which would make the result on this a negative. The actual number here should not be as large as the last one, would be negative 10,206. So again, you don't need to do these little sign things if it's not making sense to you. Just plug that into a calculator and find the actual number and figure out if it's positive or negative. Kayla, I like to use -1 and 1 a lot because it's just a simple number to plug in, but you don't always use those points. You need to go off of what your number line is. So I used -1 and 1 here because I needed a number between 0 and 2, and I also needed a number between 0 and -2. So the easiest number to choose would just be -1 and +1, especially in that case, because otherwise I'd be plugging in a decimal, which is gross. So it's not always that they're used. They'll be used in a lot of my examples because it's just a super easy number to choose, but it's not required. Hopefully that made sense. So plugging in +1 would give us a positive times a positive times something that would result in a positive, we'd have a negative to the 6th power, but a negative to a even power would give us a positive. So this would result in a positive number. It would result in positive 10,206 if you're going the number route. And plugging in positive 10, 14 times 10, 100 minus 4 to the 6th would give us a positive times a positive times a positive. So a positive, and I'm pretty sure this would be positive 1.09 times 10 to the 4th, but let me triple check. Yep, positive 1.09 times 10 to the 4th. So at negative 10, we had a negative, and then a negative, and then a positive at positive 1, and a positive at 10. So we're decreasing, decreasing, increasing, increasing. So I've run out of space, so let me shove my answer in this little box over here. You can plug those numbers into the unsimplified version. It'll give you the same thing. I just personally plug them into the simplified version because it's simplified and usually 2 seconds less to write. But you can plug it into the unsimplified term. That's perfectly fine. Unsimplified derivative if you want. So for our final answer here, notice that at negative 2, it was negative to the left and negative to the right. So it didn't change sign, so that's not a max or a min. So we don't have anything at negative 2. At 0, it changed from negative to positive, so we went from decreasing to increasing. So we must have had a local min at x equals 0. And then at x equals positive 2, it went from positive to positive, so it didn't change at all, so there was nothing there. So essentially there's no local max. So I'll just state that to make sure that we remember that. We considered it, there never turned out to be a max because there was never a case where we changed from positive to negative on this number line. So you don't have to have both. You don't have to have either. It just depends on how your number line comes out. Questions, concerns? Gone once, gone twice. All right, I'll leave this up for 5 more seconds. What we're going to do now is we're going to skip this next example. We'll come back to it on Monday to talk about a slightly different but very similar topic. And we'll do one small example of that and then we'll be out of time. So towards the bottom of this page, if this will scroll, thank you. A point at I can't read. A point at which a function changes concavity is called an inflection point. To test if a point is an inflection point, you must check if the second derivative changes sign. So positive to negative or vice versa. How we're going to do that is we're essentially going to use a sign chart similar to the first derivative test. But with the second derivative. Do not confuse this with the second derivative test. That's different. So to find inflection points, we're essentially, you can almost think about it as the first derivative test, except everything is in terms of the second derivative. So we find the second derivative. We set the second derivative equal to 0. We plug in those points on that number line, and we plug the points into the second derivative. So it's like exactly the same type of process as the first derivative test, but everything's in terms of the second derivative. So we're going to look at this first example here, and then on Monday we'll have a few more examples of all this kind of stuff. So we want to find the inflection points. The first thing we need is the second derivative. So we need the first derivative in order to find the second derivative. So we need the first derivative. So 3x squared minus 1. And then I need the second derivative, 6x. And then again, just think about it as the same type process. So now we want to take that derivative and we want to set it equal to 0. So 0 equals 6x. So x equals 0. Just like with the first derivative test, you have to check for undefined, but this is never undefined. Because there's no denominator in that second derivative. And then we do a number line, but for the second derivative, which is another reason why I like to label them. So that we remember which derivative it's talking about, which derivative to plug the values into, and all that jazz. So we put 0 on there, and we choose some test points. Something less than 0. Just for the sake of not using -1, I'll use -2 and +2. Plug those 2 points into the second derivative. Just like with the first derivative test, we don't even really care about the number, you just care about the sign. So when we plugged in -2, we got a negative, and we got a positive when we plugged in +2. Now the thing I like to do for these, now for the first derivative test, I like to draw those little increasing, decreasing lines. Here, it's not as helpful, but it does help me remember that it's not a first derivative number line. So remember, the second derivative tells us about concavity. So if the second derivative is negative, we're concave down. And then if the second derivative is positive, we're concave up. So I just kind of draw the concave pieces to remind myself what's going on in that interval. But the point is that the second derivative changed sign there. So we would have an inflection point at x equals 2. Now the nice thing about inflection points is, unlike the maxes and mins, you don't care how it changes. So with the max or the min, it depends on whether it changes from negative to positive versus positive to negative. It depends because one of them gives you a min and one of them gives you a max. With the inflection points, doesn't matter. If it changes sign at all in either direction, positive to negative or negative to positive, it's an inflection point. So that's inflection points. Again, we'll do more examples of this on Monday. I do want to babble in the last minute that I have, official minute. Let me scroll up the tiniest bit to kind of write some stuff in here. So your exam, and I'm almost done writing the practice, and I'll put that up later today. Your exam is going to cover chapters 2 through 4, but it's only going to cover up to 4.2. 4.2 is inflection points. 4.1 is local maxes and mins. So we won't get to 4.3 and 4.4, which is very sad, but whatever. So I don't really want 4.3 and 4.4 to go on your next exam, because essentially this exam is about derivatives and your third exam is going to be about integrals, which doesn't have anything to do with 4.3 and 4.4. So what's going to happen is we're going to go over 4.3 and 4.4 after the exam, but 4.3 and 4.4, that content is only going to be on the final. At 1? No. Oh my God, Oh my God. Inflection point. I butchered that. Holy bananas. I butchered that. Oh, jeez. Was at 0. Not at 2. Oh, Lord. I'm so sorry. So remember, there's the difference between essentially those kind of critical point values and the test point values. Your answer doesn't use the test points, it uses the actual points. So I'm so sorry, the inflection point's at 0, not at 2. I'm so sorry about that. Holy bananas. Oh, and now I'm out of time. If you need to run, and I'm gonna send this out in an email anyway. But the last thing I wanted to say, super duper quick. So 4.3 and 4.4 is not going to be covered. It is on your chapter 4 homework that's up right now. So what's going to happen with chapter 4 homework is it's going to be opened for 5 million bajillion years, and that's not going to be due until November 2nd. Because essentially I'm just going to leave it open until we've covered 4.3 and 4.4, and then you have the week to do it. I would suggest starting it because 4.1 and 4.2 are going to be on your exam. So doing the homework for 4.1 and 4.2 can be helpful. But since 4.3 and 4.4 we didn't get to in time, and I'm sorry that this keeps happening. This is the first semester it's ever happened to me, ever. But I'll send all that out in an email as well so that you guys remember, because I know I'm out of time technically. So if you have questions, feel free to stick around a little bit. I do have a class in a little bit, but again, sorry about that last one about my inflection point being incorrect. But otherwise, have a great weekend. The exam review should be up later today. And yeah. Stop recording.